Welcome back to The Explainer. Today, we're getting our hands dirty with the absolute foundation of CNC machining. We are dissecting the exact sequence of a perfect setup, moving step by step from a totally bare machine bed all the way to a fully calibrated system. Because here's the thing, the way you set up dictates the exact quality of your final cut. So let's unlock this workflow. Think about it. What actually separates a flawless, beautiful carve from a totally catastrophic tool crash? Honestly, the answer is almost always hidden in your setup. When we're working with these extreme tolerances, skipping even a micro step in your sequence gets magnified into ruined stock or worse, snapped bits. The stakes are incredibly high, but the good news is that the geometry is entirely in your control. All right, here's the exact chronological roadmap we're going to follow today. First, the setup stakes. Then, securing your material, the spindle safety check, navigating coordinate systems, and finally, probing for precision. Kicking things off with part 1, the setup stakes, precision versus disaster. Moving right along to part 2, securing your material, locking it down. When you're aiming for something crazy tight, like a 0.005-inch step over, locking down your workpiece requires absolute rigidity. It literally cannot move. Now, you've got a few standard options here. T-track clamps are fantastic for quick adjustments. Vacuum pods, brilliant if you're running nested sheet goods. And honestly, just driving screws directly into a sacrificial MDF spoil board offers an unbeatable hold. But here is the golden rule. Never, ever clamp stock directly to the bare metal table without a spoil board underneath. Unless, you actually want to accidentally mill your own machine bed. Now, if you want a perfectly seamless finish without those clunky clamps getting in the way of your collet, the industry has really embraced the painter's tape and CA glue trick. It's a real game changer. You just apply 3 strips of tape to your project and 3 matching strips to the spoil board. Run a bead of thin CA glue down the spoil board tape, hit the project tape with some accelerator, and press them together for about 10 seconds. The sheer strength of this is astonishing, and it leaves the entire top surface totally free from machining. But hey, for thicker stock, tape just isn't going to cut it. You need robust physical clamping. We're talking step blocks paired with clamping bars. These utilize T-slot nuts and threaded pins to create immense localized downward pressure. This is that heavy-duty workflow you need to lock down dense materials, or to secure a heavy vise directly to the machine without inducing any vibration. And speaking of a vise, when you place material inside one, you don't just drop it in blindly. You use precision steel parallels. By placing these flat bars at the bottom of the vise, you ensure your stock sits perfectly parallel to the XY plane. Plus, it elevates the material high enough to prevent your cutting tool from ever colliding with those hardened steel vise jaws. Absolutely crucial. All right, part 3, the spindle safety check. Time to tighten up. Our sources put this incredibly bluntly. A loose tool causes severe vibrations and can literally act as a high-speed projectile during a cut. Checking your spindle tightness isn't just about getting a clean edge. It's a non-negotiable safety check for your own well-being. A pro tip here, always inspect the collet cone for dust buildup before inserting the bit, and make sure to use 2 properly sized wrenches to get a hard mechanical lock. Don't just rely on the spindle lock button. Think about how this works mechanically. As you tighten that spindle nut, the collet compresses uniformly around the end mill. Maintaining that gripping tension is everything. Experts actually strongly recommend replacing your quality collets every single quarter just to maintain a total indicator runout, or TIR, of under 0.005 inches. If a worn collet introduces even microscopic runout, your bit essentially orbits its own center. That completely ruins your tool life and instantly destroys tight tolerance cuts. Moving to part 4, navigating coordinate systems. Let's look inside the machine's brain. To operate a CNC without crashing, we really have to separate absolute coordinates from work coordinates. One is a permanent map hardwired straight to the physical hardware, and the other is a custom temporary map tailored exclusively to the piece of wood you're currently working on. Let's start with the absolute coordinate origin. This is permanently locked at the physical, mechanical limits of the machine's travel. Every single time you boot up, you have to perform what's called a homing cycle. The machine slowly drives each axis to its extreme limits until it triggers the limit switches. Once it hits those sensors, it finds home, establishing its exact physical location in 3D space. But once it's homed, you actually abandon absolute space and establish your work coordinate system. You jog the machine manually so the cutter hovers exactly over your desired starting point on your stock, usually the center or the bottom left corner.
Then you just zero out the X, Y, and Z axis in your software. This creates a brand new localized origin point that your G-code will use to actually carve the part.
Which brings us to part 5, probing for precision, setting 0. Now, eyeballing that Z0 might be fine for a roughing pass, but for absolute precision, you need a touch probe. The workflow is so simple but absolutely brilliant. You position the aluminum touch plate flat on your material right under the bit. Attach the grounding magnet to the collet or the bit shank. Then, in your software, trigger the Z touch cycle. The machine slowly lowers the bit until it physically taps the plate, closing a low-voltage electrical circuit. It then bounces up and taps a second time at a slower speed, instantly calculating and locking in a perfectly flawless Z0.
But we've got to talk about a critical software quirk here that causes crashes all the time if you're not paying attention. Before you click any of those automated probing functions to find edges or Z-heights, you absolutely must ensure that Tool 99, which is the standard designation for a probe tool, is set as the active tool in your software interface. If the machine thinks a half-inch end mill is loaded instead of the probe, your offset calculations are going to be wildly inaccurate, and yeah, you're going to crash.
Okay, so your cut finishes, but the setup workflow isn't over until the post-cut quality control is completely done. Always clear the dust from the bed and filters to prevent buildup, which can actually throw off your next homing cycle. Remember, the feed hold button is your best friend if things start sounding wrong mid-cut, so don't be afraid to use it. Finally, measure your finished part with digital calipers. If you aimed for 0.005-inch accuracy and you missed it, well, your setup sequence needs a forensic review.
So, this brings us to the ultimate question to leave you with today. Is your own CNC setup ritual truly an accident-proof, step-by-step workflow, or are you just one loose collet, one unhomed axis, or one shifted piece of tape away from a total disaster? I challenge you to rigidly follow this sequence the next time you power up. Thanks for joining me on this explainer, and keep carving.